Hi everyone, this video is for week 10 of PHOT-1064, Science and Theory. It's an unusual video actually because it was actually made in the fall of 2020. All my other videos that you've been watching are probably from last year and some of them even the year before. Anyways, I just felt like I needed to do a new video for this week. Anyways, what are we doing this week? Well, this week we are talking about MTF. There we are, we're on week 10. Good to know. But what are we talking about? We're talking about MTF. And MTF stands for Modular Transfer Function. We'll look at that again in a couple more slides. But before we dive into that, we'll just do a little bit of review. And it's a bit weird doing a review when we're doing a pre-recorded video, but hopefully these review questions will give you a sense of kind of how to prepare for the final exam. Like just sort of throw a couple of these out there to you. Anyways, so here's a question that you might get on a final exam. Any lens design, and notice I put lens design in a different color. Any lens design problem that causes the failure of light rays to converge at one focus point or focal plane is known as A, diffraction, B, aberration, or C, a fatal error. What's the correct answer? Well, I'll tell you right now, the correct answer is, let me grab my comment thing here. Correct answer is, whenever we're talking about lens design, then we're talking about an aberration. Boom. It has nothing to do with diffraction. Diffraction is something completely different. Diffraction has to do with the aperture, and there's nothing lens designers can do to change the effects of the aperture. Diffraction is going to happen. It's just a matter of physics. There's nothing they can do about it. So next page. An airy disk is caused by, so if this is from last week, so hopefully you know what airy disk is. This week we do have a live session planned for week 10. So if you're not sure about airy disk and some of these aberrations, that's a good time for you to ask some of those questions. But anyways, what causes an airy disk? Is it chromatic aberration, spherical lenses, coma aberrations, or is it diffraction? And the answer here is also diffraction. So airy disk is when we talk about diffraction is this bending of light that happens when light hits an edge. But because our aperture is round, then on our sensor, what we get is something they call an airy disk. So what is diffraction? We talked about this last week. By the way, I'm going to go back up here. I put in brackets here, don't confuse it with refraction. In the past, a lot of people got those mixed up. Because there will be a question on the final exam where I ask you what diffraction is, and there'll be a time when I ask you what refraction is. So make sure you keep those straight. This is me just reviewing stuff. What is diffraction? It's when waves go through an opening, and you have this sort of bending of the waves. And since light travels in waves, then you got a little bit of bending that takes place. And because we're not talking about, in this diagram, we're looking at a wall with a sort of opening, and so you've got this sort of spreading out of the waves. We're looking at an aperture, or we're using an aperture in photography. So because that edge is round, it creates this sort of airy disk. So that's what that's all about. Let's move on. Yeah, let's forget about this slide. This keynote, or this PDF that I'm going through, is available is also on Fanch Online. So when you come to this, that's just me showing you that yes, you can actually measure what a airy disk is, but I don't want you to memorize that. Don't have to memorize that formula. It doesn't really matter. But it just shows that the airy disk gets bigger as the aperture gets smaller. So F32 would be a really small hole, and when the hole is small, the airy disk that's produced is actually bigger. So it's causing us more of a problem than with our lens wide open. Good thing to know, though. So here's another question. What is the issue with diffraction? So I've given you three options here. As the diameter of the iridescence gets smaller, the lens can no longer bring all three colors. Okay, well, I'm starting to confuse things here because I'm talking about chromatic aberration and diffraction, so that's probably not what the right answer is. B, as the diameter of the iridescence gets smaller, the detail or resolution of an image gets worse. Well, if the iridescence gets smaller, that's what we want. So the smaller the iridescence, the better. So if as the diameter of the iridescence gets smaller, the detail or resolution gets worse. No, that's not correct because we're saying it's smaller, so it should be the other way around. So number C, or letter C, as the diameter of the iridescence gets larger, yes, as the disc gets bigger, the detail or resolution of an image gets worse, and that's true. So this is the right answer right there. Which statement is true about diffraction and aberration? So I've given you two options, and they're both kind of opposite of each other, so you have to read them kind of carefully. So large apertures, okay, so large apertures like f2, 2.8. Larger apertures tend to reduce lens aberrations but increase diffraction. Something to think about. Is that the right answer or is it the wrong answer? Let's go to the next one. Larger apertures tend to, and now it's saying the opposite, larger apertures tend to increase lens aberrations but decrease the effects of diffraction. So larger apertures tend to increase aberration. So I'm going to tell you right now, this is the right answer. Okay. So this is a question that's actually on the final exam. So make sure you understand this or know this. And this also is going to help you with the project that you have to do. I have an exercise that I want you guys to do this week, and know this. If you're going to have some questions you're going to have to answer, this is the slide that you want to go back to help you make sure you get the right answers on that assignment. So large apertures, aberrations are the worst. Small aperture, the smaller aperture, aberrations tend to go away, but diffraction gets worse. So that's it. That's it for our review. So now we're going to talk about MTF. And what is this MTF thing that we're talking about? Well, this is an ad from a Canon website, and they have pages for this for all of their lenses. And this one is a 50 millimeter lens. And whenever you, and you'll see this on the Nikon website, Olympus and Sony and Fuji. They'll talk about their cameras, and then they'll have a section where they talk about their lenses. And for each lens, they'll have sort of this little promotional piece or little detailed description of what their lens is all about. They might have a sample image, and then a lot of times you'll see this MTF chart at the bottom. And that's what I want to talk about this week. So what is the deal with an MTF chart? So MTF, I guess the first thing we should talk about is what does MTF even stand for? Well, it stands for Modulation Transfer Function. And we'll talk about what modulation is a little bit later. So indicates how well the lens can reproduce the likeness of a subject on a sensor or film, sometimes referred to as its resolving power. So hopefully by now you've done the readings for this week, because they talk about accutance and resolving power and all that kind of stuff. And it's all about reproducing fine details, trying to capture as much information from with our lens as possible. So there's the real world. We take a picture of stuff out there in the real world, and then that image gets projected onto our sensor. So how much of that information, how much of that information are we capturing on our sensor? How much of the fine detail is actually being preserved? So that's kind of this is what we're interested here. So how do you measure something like this? Like, how do you measure how good your lens is? And this is an interesting problem. I mean, think about this. Maybe you have a lens and your friend has a lens, and maybe they're both 50 millimeter lenses, but yours is a Nikon, theirs is a Canon, and you're wondering which lens is sharper. So you pull up these photos of flowers that you photographed, and you said, "Oh, look at the petals! Look how all the fine detail I've captured." And your friend doesn't have any flower photos, but they have pictures of portraits. So they say, and your friend says, "Well, look at the eyebrows and look at the wrinkles in their face and all the detail in that image." Well, it's not really a fair comparison because you've got photographs of flowers and they've got pictures of a face. And for people who design lenses and people who study optics and try to improve lens design and things like that, they're not going to compare flowers to pictures of faces. They need to photograph the same thing, and that has to be consistent so if they're going to compare two lenses, they're going to want the two lenses to photograph the same thing. However, they're not going to photograph faces and they're not going to photograph flowers because they're going to have to keep doing these tests over and over again. So they can't just keep using the same flower and they can't keep using the same face. So instead, what they do is they photograph what they call line pairs. So line pairs look kind of like this. And again, if you've done the readings, you would have seen those line pairs that look kind of like this. And one thing that's nice about line pairs is you can control how small the lines are, and you can reproduce these over and over again. And now you've got an even playing field for all the lenses to compare all these different lenses because they'd all be photographing the same thing. Or if you modify a lens, change the design of it, and you want to compare the before and after, again, you would use the same set of line pair. Anyways, another thing about people who work with optics and people who study lenses and lens design, that sort of thing, and people in the science field, they like to measure things. They need to be able to measure something. So if you photograph a face or a flower, well, what are you going to measure? There's nothing to measure to sort of relay the information about how sharp something is or how good a lens performed. When you're looking at a line pair, we have black and white lines. And you can measure the brightness of a white line and you can measure the brightness of a black line and come up with a number. And then you can compare that measurement of the original scene and compare to the measurement of the scene or the recorded information that you got from the lens. So now you've got something to measure and you've got stuff to compare. So in a perfect world, and this will make sense in a moment, just bear with me. If you take a look at this diagram here, we've got two halves. We've got a left half and we have a right half. So on this side here, and I'll just put number 1. Now that's not working very well. I'll just put number 1 right here. Okay, number 1. And if we compare that to the other side, and I'll put a number 2 over here. If you compare number 1 and number 2, you've got the left-hand side is what you photographed, that's the original, and the right-hand side is the image that is projected by the lens. So this is what comes out the other end. This is what gets projected onto your sensor. So in a perfect world, those two would match. The contrast that you see, the line pairs that you see on the left, the line pairs that you see on the right-hand side, which is the image, would represent the original, what you saw in the real world. However, that rarely happens. There's always this sort of slight reduction in contrast, and you can kind of see that here, where the image on the right is starting to be a little bit less defined. That the white is just not as white anymore, and perhaps the black isn't even quite as black. So there's definitely a reduction in the contrast. So now, the people who like to measure things and like numbers, they've got something to measure. They can say, hey, here's the difference between the black and white lines, the difference in brightness of the real scene. But in the image, we can see that the difference is not the same. It's a little bit reduced. So now we've got something to measure. And maybe you've got another lens that is even of lower quality, and you can see that the contrast has been reduced even more. And you can see the white lines hardly look white at all. And, things can get so bad, or you can start making those lines closer together and increase the spatial frequency to the point where we don't even have lines anymore. It just becomes this mush of gray, in which case we've lost all resolution. So that's what's kind of handy about line pairs. It's an easy thing to reproduce, and it's a sort of an even playing field, and you can adjust the closeness of the lines. And this is just an image from some old film from the 80s. And they're talking about how good this film is, and they're sort of showing how much resolution that film can capture by showing how small the lines can get before it starts turning to mush. Anyways, let's not even worry about that graph. It's not really that important. So let's get back to MTF. So modulation transfer function. A perfect optical system, aberration-free, imagine the perfect lens, would not reduce the contrast of an image. So getting back to this, in a perfect world, the graph on the right would match the one on the left. The image would match the real life version. So a perfect optical system would be aberration-free, would not reduce contrast in an image. However, in real life, there is no perfect lens. And there's going to be lens flare. There's going to be lens design issues. There's going to be internal reflections. We'll talk about internal reflections next week. There's irregularities, there's aberrations, there's coma, there's astigmatism, and there's all these other issues. All of these things degrade the image. And so instead, we get sort of this reduction in contrast. And that's what we were looking at here. We see this reduction in contrast that takes place. That's what pretty much always happens. So a line pair undergoes degradation as the spatial frequency increases. So as those line pairs, and that's the other thing, not only do you start to see problems with lens quality, but as the line pairs get smaller and smaller, and we're measuring how good that lens is at reproducing those fine details, you sort of get this reduction in contrast, and we call this modulation. A line pair undergoes degradation as the spatial frequency increases. In other words, the image pattern is degraded in contrast until the pattern cannot be distinguished. The lines disappear and become gray. Well, anyways, the reduction of contrast is known as modulation. So that is this sort of loss of resolution, if you will, where we can no longer make the line pair. So this might help us understand this a little bit better. But if it doesn't, there's always an opportunity to send me an email and ask questions. But here's kind of me just saying the same thing, just with a different diagram. On the left-hand side is our object. That's the real world. And there's our line pair right there at the top. And imagine we had some sort of meter, some kind of maybe a light meter, or some sort of measuring device, and we were measuring the brightness levels. So black line would be 0, and then there's an abrupt change, and then we're measuring white, which is represented by this higher line. And then it drops back down to 0, then it goes back up to, pick a number, 100, 255, doesn't matter. And so you've got this 100% contrast between black and white. Perfect, okay? But this is the real world. If we go over to this side where we have the image that's being projected, from the lens. And usually what's being projected is never as good as the original. Keep in mind, this diagram is extremely exaggerated. It's obviously not going to be this bad, especially blown up to that size. But let's just see what's going on here. In real life, you don't have this, even though this is what you photographed, you're not going to get this perfect representation. Instead, what you're going to get is black. And then you'll get, black, and then you're going to get white in the middle. But right here in between those, you get this sort of transition from black to white. And that's represented by this sort of slope on our little graph here. So we don't have the hard edges that we have over here. We sort of get this gradual, this sort of pattern that you see here. And not only that, if you look at the peaks and the troughs, they're not as great as they were here. There's a bit of reduction in contrast. So in this case, we're only seeing 90% contrast. Here we can see the line pairs have gotten even closer together. So there's the spatial frequency has increased. There's more lines per millimeter. And we've gotten to the point where we don't even have black anymore. And so you get this scenario where the contrast is greatly reduced. So some of this is beyond the scope of this course, but I just wanted you to get a sense of the fact that, hey, there's something that we can measure with line pairs, and we can start to see this change in contrast, and now we have something to measure. And here's just sort of another diagram. The top is reality, and below is the image. And you can kind of see we're getting a pretty good representation of the contrast. So we have an MTF of 1, and then things just start getting lower and worse and worse and worse as our line pairs get smaller and we start to lose contrast. So that's just me trying to illustrate to you kind of what's going on here. And again, don't overthink this. I'm not going to put this diagram on the final exam. I just want you to sort of think about what are line pairs telling us, and what's it could possibly be used for. And now that we've looked at that, let's go back to our MTF graph. So what do we need to know about these MTF graphs, and what's it telling us? So let's go through this step by step. So this is, I'm going to make this bigger. Hang on a sec. Let's do that. Does that make it any bigger? A little bit bigger. So let's look at what all the different, what this is telling us, because there's a lot of information here. We've got lines, some are blue, some are black. We've got numbers here on the left, and we got numbers along the bottom. So let's start with the numbers here along the bottom. And it goes from 0 to 20. In fact, it actually goes to, probably better to think of that as about 21.5, and I'll explain why in a second. And that would be right at the end here. Horizontal axis is the distance from the center of the image towards the corners. So what is that all about? What does this mean? So this is our sensor. So that's what this is representing to us here. There, that red circle is our image circle. So inside of our camera, that's the image circle that's projected onto our sensor. And then in our sensor, we've got an image, and it's within that rectangular frame. Well, if we wanted to know how good a lens is performing, we don't just care about the center. We also care about what's happening in the corner, okay? Not just the center. Let me see if I can do the center here. Not just the center, but also up in the corner. And one thing that you might have recalled from last week, that things tend to be sharper in the center. And as you get towards the corners, that's where the problems really become more visible. So if we're going to graph the quality of our lens, we're probably interested in what does the image look like in the center, and we're also interested, excuse me, in what does the image look like in the corner and everything in between. So the bottom represents that range of distances. So 0 is right here, right smack in the middle. And 21.5 is here in the corner, okay? And while we're looking at this, I just want to point out one other thing. You'll notice that in my diagram, I've got 24 millimeters by 36 millimeters. And, a couple weeks ago, we looked at what a standard lens is, and we said, well, you got to measure, you got to figure out what this diagonal is. And, a squared plus b squared equals c squared. And this, on a full frame sensor, that whole corner to corner was 43 millimeters. Well, cut 43 millimeters in half, and you've got your 21.5. Okay, that's well and good. Another thing that I want to point out to you is the black line here represents a full frame sensor. And if you have a crop sensor camera, that's represented by this blue rectangle. So your image circle is actually a little bit smaller. So the reason I point that out to you is because if you have a crop sensor camera, this distance is probably closer to 14 to 15 millimeter. So on this graph, we only really have to worry about going up to here because because you're not your sensor is not even recording what's going, this part of your image. That is if you're using a regular lens on a crop sensor camera. Some cameras manufacturers make special lenses just for crop sensor cameras that only fit on crop sensor cameras. Then what I just showed you doesn't really apply, because your MTF chart would not even go up to 21. It would stop at about 14. But anyways, I'm just trying to point out, so we're going to come back to this later on as we go through this keynote. Let's move on. Oh, sorry, another thing I want to show you is see the line pairs, and I put line pairs in here, and I put line pairs in the corner. So it's just showing us that we're measuring that contrast at those different locations and the locations in between. So that's what the line along the bottom is. The vertical numbers, this vertical axis, goes from 0 to 1. And 0 means you've lost all contrast. That is, take a look at the bottom of this graph over here where we said 20% contrast. So that would be here. So these two represent each other. And this one is 90%. And so that's over here. So the higher the number, the better. The closer we are to 1, the better things are. Okay, so if I go back to this graph here, and we're measuring the contrast between the black and white lines, 100% means we've matched the original. 90%, for example, means we've lost about 10% of our contrast. The higher the number, the better. And we're measuring in the middle, and we're measuring in the corner, and everything in between. So that's what those two axes mean. So the other thing that I'll draw your attention to is there are some blue lines, and there are some black lines, and there's some solid lines, and there's some dashed lines, and there's some thick lines and thin lines. So let's talk about those lines. So first thing we'll talk about is the fact that there's blue and black. So the blue lines represent when the lens is at f8. The black lines represent when the aperture is wide open. So we're testing our lenses at those two apertures, okay? And you'll typically notice that f8, the blue lines are typically higher because the lens performed better at f8. On a lens, when the lens is wide open, that's when things are the worst. So aperture is the worst, chromatic aberration is the worst, the performance of the lens is the worst. So there's going to be more reduction in contrast. So you'll notice the black lines tend to be lower and the blue lines tend to be higher. And you'll see that with most MTF graphs. So why f8? Because f8 is somewhere in the middle. Wide open, you've got aperture problems. Small aperture, you've got diffraction is a problem. f8 is kind of that sweet spot in the middle. Aberrations are not as visible, yet it's not so small that diffraction is an issue. So you're kind of in between both of those two extremes. And that's why lenses tend to perform better when you're at the middle aperture. And so photographers a lot of times call that the sweet spot of the lens. And you'll hear that term come up a lot. One thing that you'll notice is there's no third color. Why isn't there a color for a small aperture? And maybe that's something we'll talk about during our live session on Thursday. Anyways. So the other thing you'll notice that there's some solid lines and there's some dashed lines, or broken line is another word for dashed lines. Well, that's because they also want to sort of measure how good the lens is doing at handling astigmatism. So you might recall last week we talked about astigmatism, and that's where lines that go one direction have a slightly different, sharpness value of lines going at a 90-degree angle to that. So They're called the tangential and sagittal lines, or sagittal or meridional lines. And again, that is just a throwback to what we talked about last week, where we talked about this astigmatism, where, and this diagram kind of illustrates it really well. Where, and if you look at the bottom right over here, we have vertical lines that are fairly sharp, but then any of the lines that are horizontal, they're not quite as sharp. And then if you correct for that problem, then you get the opposite, where vertical lines are now fuzzy and the horizontal lines are sharp. So that's this weird astigmatism. Usually what lens designers do is they try to compromise and figure out where they can try to make them both look half decent. But at the same time, neither one is perfect. But anyways, so that's our sagittal and tangential. And I just can't stress enough, we always see these lines as being, if you look in the corner there, it looks like they're just 90 degrees to each other and always that direction. But really what this line right here, for example, is representing these lines that go this way, kind of like the rim of a wheel. And these lines here that go this way are actually representing these lines here that are like the spoke of the wheel. Okay, so just keep that in mind, just make sure we get that. So that's why we have solid lines and broken lines, because, and you don't have to memorize, this is not going to be on the test. I don't want you to know what solid lines and broken lines are, but do know why do we have these two solid lines and broken lines. This is because we're checking for astigmatism. Okay. So the other thing that you'll notice is there are bold lines and thin lines. So the bold lines are when there's 10 lines per millimeter, and the thin lines are 30 lines per millimeter. So the thin lines, it's a higher spatial frequency. There's more, the lines are smaller, the detail's finer. So again, you'll tend to see the bold lines higher and the thin lines lower, because now we're dealing with really fine detail. And that's, again, where we start to see this modulation is starting to really become visible. Anyway, so that's what the bold and thin lines are all about. So there you go. Lots of information in this little graph. It's telling us a lot of things. So when you look at these graphs, what are we checking for? Well, the closer to 1, the higher the lines are, the better. That means it's preserving as much contrast, more contrast of that's existing in the original scene. So higher is better. What's our next thing? I'm going to go back to this for a second. The other thing that we want to look for is what's happening in the corners. Is that high quality that we're seeing over here, look at this, is it staying up there all the way to the corner? And this lens right here is performing quite well. And remember, blue lines are f8, so they're higher, and it's looking pretty good all the way to the corner. When you're wide open, which is what the black is, we can kind of see things start to get a little bit weird. We start getting some astigmatism, and we start to see this degradation in the image in the corners. And when we get to the really fine detail, things get a little bit weird, but it's still a pretty impressive lens. And this just sort of shows us gives us some ideas of some numbers. So 0.8 is like amazing, but 0.6 to 0.8 is still considered a good lens. So don't get too stressed if you look at your lens and you're shocked by what the MTF graphs look like. The closer the sagittal and meridional lines, or the solid and broken lines, are, the better that camera is doing solving the astigmatism problem. So that's more what I'm interested. That's the kind of thing I want you to know for the final exam. It's not so much what solid and broken stand for, just know the significance of those two, the solid and the broken line, what it's telling us. MTF graphs, another thing to think about for MTF graphs is curves of a lens should only be compared with those of a lens of identical similar focal length. So, some of you are just going to dive into this. Some of you guys are going to be like, yeah, I don't care about MTF graphs. Glad I know how they work, but that's about, and you're not going to worry about it too much. But some of you are going to get right into it, and you're going to start analyzing all your lenses. And you're going to start analyzing your lens compared to your friend's lens and whatever. So one thing to keep in mind is if you start analyzing or looking at MTF graphs of your lens and you want to compare it to a different lens, typically you would only compare the same focal lengths. You wouldn't compare a 50 millimeter lens with a 100 millimeter lens because that's comparing apples and oranges. However, you might want to compare it to 50 millimeter lens, so maybe a Nikon lens and maybe a Sony lens, and compare the two and see which one performs better. But you want to compare the similar focal lengths. Another thing too, before you get too hung up about MTF graphs, because you can start looking at them and start feeling really bad about your lens. Oh my gosh, the MTF isn't all that great. But one thing you should keep in mind is a lot of these lenses that have a great MTF graph, they're also quite expensive. And so you have to think about that too. Another thing too, some of these lenses that perform really well, they're big lenses, they're heavy. Their front lenses are usually quite large. And there's a lot of lens elements to do all the corrections that are necessary. And if you photograph a wedding all day and you have a heavy lens hanging around your neck, well, that's not a good thing either. So you kind of got to weigh the pros and cons. Maybe, what's the most important thing to you. And if it's a lens that you're using in the studio and you don't have to carry it around, then yeah, go for the heavy lens. Who cares? But if you are going to be carrying a lens around all day, well, okay, you might have to sacrifice some of the quality because you just want a lighter lens. Price is a factor as well. Good lenses come with a really high sticker price. So again, you got to start, especially when you're first starting out, you got to ask yourself, how deep into debt do you want to be to buy all these amazing lenses? And are you getting a return? Are your clients noticing that difference? So there's a lot of things that you have to consider. So here's some examples here's a couple of 85 millimeter lenses. And the 85 millimeter 1.2, this is a Canon lens, by the way, L series lenses. L series means it's their higher end lens, more professional level. Well, that 85 millimeter is a desirable lens. That lens costs about $2,700 just for that lens alone. And but if you look at the MTF graph, I mean, look at that line at the top. It is practically straight right to the corners, and it's up fairly high. Compare that to this lens here, which kind of starts to take a dive down in the corner. But this is a lens, this particular graph is for a lens that is designed for a full frame sensor camera. So here's something I was talking about earlier. Remember what I said about if you have a crop sensor camera? You don't have to, your sensor stops here. The size of your sensor is smaller, so you're not even seeing this part of the image. So you really only have to worry about this part of the graph. So if you have a crop sensor camera, this would be an amazing lens. So it's not as good as this lens, but on a crop sensor camera, that is an amazing lens. And it still has a wide aperture of 1.8, so if you want to have shallow depth of field and all that. So stuff to think about. That's just me thinking out loud of some of the things I would think about if I was looking at this MTF graph. Let's jump ahead here. So here's another thing I should mention too. When you look at zoom lenses, they'll typically show two MTF graphs, one wide open and one when the lens is zoomed in. So, and you can compare, how does the quality change when you're zoomed out compared to being zoomed in. So here's a real life example. We had a student, this is going back probably about 10 years ago, and this student was going away on a trip to Africa. And so he was trying to figure out, his parents had given him some money so that he could go purchase a lens, and he wanted to buy a zoom lens because he could only buy one lens. We couldn't buy a whole bunch of lenses, so he's going to get a zoom lens. And so so he's looking at these two lenses, and he was trying to figure out which one to buy. And I remember him coming into talking to all the professors, saying, "Hey, what do you guys think? What do you guys think?" And anyways, what the student ended up doing was going to the store, and the people at the store agreed to loan him both lenses for the weekend. And so here's the two lenses that he was looking at. So 70-300 100 to 400, so kind of the same zoom range. Both of them have a similar maximum aperture, and the only thing different is the lens on the top had image stabilizer, which is very appealing because if you, hopefully by now you know what image stabilizer means. It means you can handhold the lens at a slower shutter speed before, and there's some technology in the lens that's helping it prevent it from vibrating, if you will. So your pictures, you can go without a tripod at slower shutter speeds. Anyways, so this lens was IS, but the bottom lens, even though this photo has image stabilizer, that's not the right photo, but it's an L series lens. So typically the optics are better and the build quality of the lens is better. So anyway, this student had to make some decisions, deciding what is most important. So if we were to look at the MTF graph, if you look at the L series lens, it is definitely a better lens. It has less of a astigmatism issue. I mean, look at these lines, how they just sort of go apart, especially up here. These blue lines, wow, there's a lot of deviation taking place there. The lines are staying together better over here. Both of them kind of drop off in the corners. That can't really be helped. But at least with the L series lens, at f8, things stay pretty good right across at both focal lengths. So the student did another really cool thing, is he went out and did some testing, and he tested zoomed in and zoomed out. So he did a test at 300 and he did a test at 100 millimeter. So you can see, and I'm just going to go to the next slide. We're going to zoom in here. You can definitely see on the right-hand side that image is sharper. And that's, not surprising just by what we saw when we looked at the MTF Chart. And this is the L series lens right there. You know what, maybe I'm wrong. Maybe that lens was also an IS lens. Anyways, doesn't matter. So this was an L series lens compared to the other one. This one had the better MTF graph, and you can kind of see the detail in the wood is just a little bit sharper. Let's go to the next example. So this is another scene that he shot. Now this is at the other range at, I think he shot these at 100 millimeter. Yeah. And this is a great scene because you've got the detail in the trees. You've got this grass here with these vertical lines. So it's almost like it's got built-in line pairs right in his image. And so we're going to look at the outer edge here because we want to get away from the center and just see how these two lenses perform. And, very dramatic. Like, look how, and I'm going to see if I can zoom that in, make it you guys see a little bit better. But look at the trees, the branches, and the one image on the bottom is definitely sharper. Look at the grass at the top and look at the grass at the bottom. So much more detail on the bottom. So that's kind of what the MTF graph is telling us, like how good is the lens going to perform there. And so we looked at the MTF for this lens, and then I said, just by looking at the graph, it seems to me that the L series lens is better. And then the proof is in the photos as well. So we were able to see it there. So, so appreciative that student supplied us with those files. Here's another cool thing while we're talking about MTF. There's websites where you can download files, and this image at the top was from this one website. His name is Bob Atkins, I believe. If I can find the link, I'll put it on FOL for you. But he has this file that he recommends that people download. Download it, print it, go to a printer and print it, and then put it on the wall and take pictures of it and see how the line pairs perform. And you can kind of see that there's definitely a difference in the image of these line pairs. And if you look at the left, look at how the number 9 has got a bit of a kind of a magenta or bluish cast to it. And that's the chromatic aberration starting to become visible. And that's at 5.6. But as the aperture gets smaller, the chromatic aberration starts to disappear. However, the image starts to become a little bit softer as well. And that's where we have this whole issue of diffraction starting to be a problem. So interesting, and that kind of ties into the assignment that I've got you guys working on this week. Also notice that, again, there's the lines, they're at 90 degrees, and that's because it's representing the tangential and sagittal lines. Anyways, yeah, I'll just move ahead here. So that's pretty much where I kind of want to wrap this up. You know, there's just something about photographers, and it's not all photographers, but a lot of us just love our lenses, and we love for them to be sharp. The sharper our lens is, the more that we can blow it up into a larger size, the happier our clients will be. But you don't always have to worry about those things. There's some people who all their images are only ever end up online. Nobody ever zooms in on them. So maybe for them, sharpness is not that big of a deal. But I know for me it is. Just one of those guys. And you know, this is a picture of my daughter from about, probably about 10 years ago now. And boy, I just remember I just bought a 70-200 L series lenses, and I was just testing it out. And the first thing I did was just zoomed in and was just amazed at how much detail is being captured. And look at the eyelashes and the strands of hair. Just awesome stuff. But anyways, that's me getting all excited about lenses. So this week we have an assignment very similar to what we did here. Instead of photographing line pair, I'm going to have you guys photographing text, but that's in a whole nother video. Hopefully some of you will be able to join me on Thursday. If not, the live session will definitely be recorded. Anyway, thanks for watching. This is week 10.